Imagine designing a sensitive electronic circuit where every voltage needs to be just right. What happens if an unseen factor silently starts to drift your critical reference points? This kind of stability challenge is precisely what engineers consider when working with Zener diodes. Temperature significantly affects a Zener diode's breakdown voltage, and this influence depends primarily on the magnitude of the Zener voltage itself. Specifically, Zener diodes with breakdown voltages below 5 to 6 volts typically exhibit a negative temperature coefficient, meaning their breakdown voltage decreases as temperature rises. Conversely, Zener diodes with breakdown voltages above 5 to 6 volts generally show a positive temperature coefficient, where their breakdown voltage increases with rising temperature. This dual behavior stems from the two primary mechanisms responsible for reverse breakdown in a Zener diode: the Zener effect and the avalanche effect. The Zener effect, which dominates in lower voltage Zener diodes, is a quantum mechanical phenomenon involving electron tunneling across the depletion region. As temperature increases, the energy band gap effectively narrows slightly, making tunneling easier and thus reducing the voltage required for breakdown, leading to a negative temperature coefficient. In contrast, the avalanche effect, prevalent in higher voltage Zener diodes, occurs when thermally generated charge carriers gain enough energy in the electric field to knock other electrons free through collisions, creating an avalanche of carriers. Higher temperatures increase the frequency of lattice vibrations, which means charge carriers experience more collisions. These increased collisions reduce the mean free path of the carriers, requiring a higher voltage to accelerate them sufficiently to cause new ionizations, thus leading to a positive temperature coefficient. The interesting crossover point around 5 to 6 volts is where both effects have a comparable influence. Here, the positive temperature coefficient of the avalanche effect can effectively cancel out the negative temperature coefficient of the Zener effect, resulting in Zener diodes with very stable breakdown voltages across a wide temperature range. This characteristic is precisely why diodes in this particular voltage range are often chosen for precision voltage reference applications. To effectively account for temperature in your designs, first, always refer to the manufacturer's datasheet for the specific temperature coefficient, often expressed in millivolts per degree Celsius or as a percentage per degree Celsius. For critical applications, consider using temperature-compensated Zener diodes, which are often composed of a Zener diode in series with one or more forward-biased diodes to create a composite device with a near-zero temperature coefficient. You can also implement active temperature compensation circuits to maintain stability. Understanding these temperature dependencies is crucial for reliable circuit performance. By recognizing whether your Zener diode operates primarily under the Zener or avalanche effect, and knowing how to interpret temperature coefficient specifications, you gain a powerful tool for designing robust and stable voltage reference systems in varying environmental conditions. This knowledge empowers you to build circuits that perform consistently and predictably, no matter the ambient temperature.